Hi, I think we should just get started. Cool. Hey, everyone. Thank you for joining in for the first session of the LLMs and Transformers reading group. My name is Basil, and co-leading this reading group with me is Ashley. And just a fun fact, Ashley's off a 16-hour flight from Vancouver to Switzerland, but she's a trooper. She was adamant on making it, so thank you so much. Just a quick overview of what these reading groups are going to be. We're going to be hosting 3 sessions every other week starting from today, where Ashley and I are going to be going over 2 papers related to LLMs and Transformers. Before we get started, while Ashley and I are going to be selecting and presenting papers for every other week, if anyone's interested in seeing a specific paper be presented, or if anyone's interested in presenting a paper themselves, or if anyone wants to present but doesn't have a paper in mind, just let us know. Give us suggestions, messages on Discord or through Instagram or whatever. And yeah, we'll make sure to set that up. So let's get started with the first paper of this session. Ashley's going to be presenting a paper on Orca.
Yeah, thank you. So I'll hop right into it. Just a bit of an explanation about why we're talking about this paper. It's been really recently released and made all sorts of news headlines over the last couple of weeks. It's called Orca Progressively Learning from Complex Explanation Traces of GPT-4. And the background you'll need to kind of know what's going on here is that, as we all know, OpenAI has had a lot of success with their models. So they had GPT-3 that led into ChatGPT, which was kind of like GPT 3.5, and then GPT-4. And it's been really expensive to train these models, and they're not open sourced. But these sorts of models do become what we term large foundational models, because they're extremely large models trained on a really wide variety of data to accomplish a bunch of downstream tasks. And then there's also Meta's Llama models, which have also been a pretty big success. They were released in several different sizes that are smaller than the OpenAI models, and they became open sourced through a leak, so we actually do have access to them. And one of the interesting first bits of work in this area was called Stanford Alpaca, where a group at Stanford actually took the smallest Meta Llama model and fine-tuned it with a bunch of examples made with GPT-3, and that cost them under $600 to do. And while they weren't able to get something that was as good as GPT-3, they got something that was better in performance than Llama and quite impressive, given it was only $600 for them to kind of create a model like that when other people have invested many more resources. The last I checked, it wasn't like an easy, you can now go and download this model, but the code was available on GitHub to kind of guide people who were interested in doing similar things through how they could do it themselves. Then a more recent effort is the Vicuna chatbot that was based on a slightly bigger Llama model, the 13 billion parameter one. And it was created by a bunch of researchers from US universities. And it's actually easily able to be downloaded using pip or GitHub. And how it works is it takes a bunch of example conversations people have had with ChatGPT through this website called ShareGPT, and it fine-tunes the Llama model based on those, and then it evaluates how good the responses are using GPT-4. So then what is this model doing? It's also based on that same 13 billion parameter Meta large language model, and it's created by researchers at Microsoft. And it tries to learn from more rich signals, they call it, of GPT-4. So not just using GPT-4 to assess if the answers was good or bad, or give example answers it should have had, but actually do more complex explanation traces and step-by-step kind of thought processes for how it goes about getting to the conclusion that it usually gives as a final output. And they also use this more unique technique where they had ChatGPT help with some of the intermediate training for less complex things to have even more diverse inputs. So the existing fine-tuning method, these things like Alpaca and Vicuna that we've been talking about is outlined in broad strokes here, where you have the training data consisting of some instruction and then the answer. So very simple, very straightforward. And this is the easiest thing you could think to train on. So you have like the instruction, the more specific input that you want, and then the answer. Then something like GPT-4 processes that to give you this answer, and that's what you use to kind of try and train against and get your answers being similar to. The quote at the bottom is taken from the paper where they say, "A lack of rigorous evaluation resulting in overestimating the small model's capability as they tend to learn to imitate the style but not the reasoning process of the large foundational models is one of the interesting downfalls here, because GPT-4 is going to then favor responses that are really similar to the kind of responses it would give, even if they don't necessarily mimic like a reasonable thought process. If they just mimic the sort of style it outputs in, it's going to favor that. So this new Orca model, what it does, I don't actually expect you to read any of the text here, but notice that there's a lot more of it. So one of the things that we talked about last term with the GPT-4 paper was the introduction of these system instructions, where you have another way to input information to the model on what kind of outputs you want. So it really heavily uses these system instructions to give the tool like GPT-4 some background on what kind of response it wants, and that it wants it detailed step by step and very logical. And then it'll use the same sort of user instructions and input, but the output it gets is now very discreetly in steps that mention everything you would need to understand the problem and kind of connect the dots for a model that might know a lot less. So how well did this do? The cool results to see off the bat are that using the same evaluation set with GPT-4 in this top right-hand corner, the plots here show that the Orca model actually does better than Vicuna on its own evaluation set. And then it does better than all these other models we've mentioned as well, like Alpaca and the base Llama 13 billion parameter model. So that's quite impressive, and it's performing at very comparable levels to ChatGPT. Then here on the bottom left, you can see a similar thing where it's really far surpassing Vicuna, but performing similar to ChatGPT. And we're talking about something that took a lot more resources to create, and it's a lot bigger of a model, and it's able to get similar performance. On this one at the bottom here is called the Big Bench Hard evaluation set, and it tries to really get at the core of what these models usually struggle with in terms of like large language models and their reasoning, and really challenge it. That's why it's called Big Bench Hard. Then on the right, these are also areas, these academic exams that large language models often struggle with because they require a good amount of logic and they're not very straightforward answers all of the time. So here we see that Orca does underperform ChatGPT and performs similar to GPT-3, which is this one here, and still a lot better than Vicuna. So it's been a huge leap forward, I think, seeing these results. And just to dive a little more into them on the academic exams, what you'll notice from this plot is that the blue line shows the average human understanding and how well average humans do on these academic exams listed here. And you'll see that, like, if any of you guys have tried to get ChatGPT to answer like your math homework, that's somewhere it can really struggle with. And you can see that here, that these large language models, none of them are able to do the sort of more rigorous math that you would see come up on the GRE in nearly the same way as humans would be able to. But then in these more language-based ones, they can perform really well And Orca does perform very similar to ChatGPT, just slightly worse in all areas. And GPT-4 performs better than all of them. And then on the Big Bench Hard, we see a similar scheme of things playing out where GPT-4 is the best, but Orca and ChatGPT are really comparable. And here, Orca's maybe even doing better at more spots when you see these green parts jet out a little further into the higher numbers. So one of the big concerns that we have with these models are hallucinations, and that they often can give untrue and biased answers. And so that's something that we really want to optimize for in up and coming models. And so there's been done some analysis here where they use this truthful QA data set that is often supposed to really get to testing some of these hallucinations and biases. And you can see that Orca, once again, outperforms Vicuna, but doesn't do as well as GPT-4 or ChatGPT. So the last thing we'll touch on in the results section is just toxicity, which is also a big thing we want to get better at for new models. The more powerful they are, the more used they are, it's better that they're less toxic. And there's this specific data set called Toxic Gen that has a bunch of prompts that could potentially give toxic outputs. And then there's a hate speech detector called HateBert that they use to quantify the probability that that's a toxic response that it has. And I don't expect you to read all the things at the bottom here, but what it shows is that Vicuna, the bars are higher consistently on this toxic content analysis, meaning that Vicuna is often creating more toxic content than Orca, which is great that we've then made, they've made some progress into making something that produces less toxic outputs. And we'll just touch on limitations here. There's ones that exist for all large language models, and we've talked about, right? Like bias, hallucinations, toxicity. And there's also often a lack of contextual understanding. They don't, unless you're explicitly giving them the background they need, not able to actually go and retrieve very specific information or even know very up-to-date information. Those are huge drawbacks of using these models. And then there's not a lot of transparency because they are so big. It's a lot of a black box sort of situation. And given how accessible they are and powerful they are, there's also the potential for misuse, especially when we don't have those first points completely under control. But this paper does highlight some more specific limitations to these sorts of models. And the first you could assume is that they inherit the shortcomings of the teacher model. So here GPT-4 is used as the main teacher, and anything that's wrong with GPT-4 is probably also going to be wrong with something like Orca. And they were also able to really probe that these smaller models have less ability to memorize than the larger models. So when you want to recall specific information, the larger models, although they can't still do that well, they can do it better than a smaller model. And then this paper tested a lot of what we call zero-shot learning. It'll give, an example, then ask a question, or give some data, then ask a question, and want the correct response. And it hasn't really been probed on how a model like this works beyond that, especially with something like multi-turn conversations. And then the last thing is, it seems like the performance is really based on whether the data was common in the distribution of the training data. So things like coding and math weren't very common in the training data that Orca was given, and so it's not expected to perform particularly well there. So I just wanted to leave us a couple minutes to discuss this. If anyone had anything they wanted to bring up, any thoughts, any questions. One of the things I want to toss out there is just reading about this. One of the questions that I saw came up that I think is really interesting to talk about is Microsoft obviously funds a lot of what OpenAI does and would be funding any new ventures like a GPT-5 that would be extremely costly. And so I think that there's some thought that this work they did in terms of seeing if you can actually mimic the reasoning using something like Orca. If that they're maybe looking into because it's part of if they're deciding it's worth another big investment to make a much bigger model, or if they would just be able to copy from someone if someone else made a better model and could just fine tune on that. So I do think it gets to the heart of this question of like, are we going towards bigger and bigger models, or is something like this maybe going to be our shortcut to not have to keep on going larger and larger with the models? So I'll toss that over to you guys. And interested to hear if anyone has any thoughts.
Yeah, I do think like right now we are seeing more and more improvements, like as you're going bigger and bigger, like with the models, you know, the bigger the model, the better generally the performance we're seeing. But of course, like it is costly to just like train up larger and larger models, and it is like more computationally expensive. So it would make sense for them to like try and target smaller size models. Plus, also like when you think about it, I saw this like factoid the other day. The brain itself has 89 billion parameters, where something or parameters sorry has like 89 billion neurons, where something like GPT-4 was like rumored to have trillions of parameters, but still isn't able to like think as logically as us, and like that model isn't as general or as flexible as our brain is. So I think there should be like more heading towards models that are smaller in the number of parameters, but they're able to like get more juice out of them. I guess that's like my thoughts on it.
Yeah, I also I think that I was actually like looking at the number of parameters in the brain like a few days ago. I was just curious at least how it compared, and I think we are still like maybe an order of magnitude behind, or actually I think I was looking at GPT-3, so maybe GPT-4 is actually even closer. But yeah, I know Yoshio Bengio was talking about kind of exactly what you were saying, Basil, and that there needs to be like a bit of a paradigm shift in the way that models are trained, because and kind of make them slightly more similar to how humans learn. For example, like when humans are learning the differences between like different types of animals, we don't need to see tens of thousands of images to be able to decipher that. And right now we're kind of taking the approach of just throwing enormous amounts of data at these models, and we're getting pretty interesting results. But I think to make like, or he's a proponent of the idea that to make really more meaningful improvements, there needs to be a little bit of a change in the approach we're taking to training these models. But yeah. Also, just in terms of the applications of like Orca, and because a lot of these, like a lot of edge devices, like if you have a cell phone, right, your cell phone doesn't have like the computational resources to be running like these massive models, right? So you're usually limited by the I mean, that the number of applications are awesome, but think about if we could have these models be working on your laptop or on your cell phone. And so I know there's I'll actually link this other paper I was like proposing in the chat that was talking about like a new way of compressing large language models without like significantly. They were claiming that it was approaching near lossless compression, which is pretty amazing. So yeah, I don't know if anyone wants to check it out. I thought it was a pretty cool read.
This is really interesting. Sorry for being on mute. But I know, like, I feel like last reading group we talked to, like last term's reading group, one of them, I think it was Abby who presented on like Milan, which was like going in and auditing the neurons to see which ones were actually doing anything useful and sort of trying to compare textual descriptions to what the neurons were doing. But it was cool, like I think in that paper they did talk about like how you can have ways to tell if the neurons are actually doing anything useful. And that would be cool to kind of go in and be like, what is ones we maybe don't actually need and prune them off. And the other thing I'll say, I know we mentioned it at the past workshop, but I think the smaller models, like even if they have these like small, like lesser abilities when it comes to like actually just like knowing facts and everything, I feel like that paired with a lot of the tooling we're seeing of like being able to hook them up to a database or hook them up to a search engine, then just really makes up for any discrepancy with not actually being able to know facts. And so I think that that's kind of nice in terms of like, that's even better if you can actually just go right to the information source than have it retrieve it from some sort of abstract memory it has just because it's a huge model.
Cool.
Yeah, that's pretty
nice. One other quick question I had was the idea of like instruction tuning and explanation tuning. That seems pretty interesting. But I think the explanation tuning was generated by GPT-4. Like, are there other well-known models that use these techniques, or is this like kind of a unique tuning method that Orca was using? Or maybe I missed something in the paper that discussed that.
The unique part of the Orca stuff was just that it was actually getting it to explain its reasoning process. I think every other attempt to tune something like this is just like, what's the question, what's the output? Where here, the model actually has to kind of output a reasoning process that is comparable to what GPT-4 would do. And it seems like other people have used GPT-4, but not that much because it is so recent. But what they did that was cool is they would use like, in not all the experiments, but some of them, they would use ChatGPT as like an intermediate teacher where it would explain like everything that it could. And then once it kind of got a bit too complex, GPT-4 could come in and add, but it was kind of a cool two-step process.
Right.
Not sure if that answers the question.
Yeah, because I saw that GPT-4 was generating the explanation, which that makes sense. It's also cool because I think it performed better than GPT-4 and ChatGPT with respect to the toxicity. I saw that that graph was pretty cool.
Yeah, and I think with the fail rates of like the amount of times it was able to do better on those. So that's cool. Okay, well, thank you guys all for listening and having such a discussion. I'll pass it over to Basil for his presentation.
Hey, yeah, so just, sorry, 1 second. Something missing each time. So yeah, heads up, this meeting will be recorded and we are looking to just share maybe on our YouTube channel or on our Drive and elaborate if there's something else we need to do and come for each time. So it's going to be a bi-weekly session, just to go over that again. It's going to be a bi-weekly session for the next, bi-weekly session just for like 3 sessions. Ashley and I are going to be presenting 2 papers or like 2 papers each session. However, if you are interested in presenting a paper yourself or you want to see us present a specific paper that you're interested to know more about, yeah, make sure just to message us on Discord or Instagram or any other medium. Cool. Yeah, so going over to
just before you move on, someone just has their hand up. I'll just call on them just in case.
Oh, yeah.
Hi, I just have one quick question. Is there any fundamental reason that the large language model are not excelling at reasoning, like logical reasoning?
I think I'd love to hear other people chime in on this, but I'm sure it's just that it's not like fundamentally what they were trained to do, and like they're trained to just like put language together. Reasoning is like a thing that might emerge from that, but when they're just trying to kind of optimize like what text next to each other is most likely, it's different than like a more mathematical model that's actually supposed to like build some sort of actual description of what's going on. So I think that at the heart of it, it's probably that. And that so far, I think they've surpassed what we thought for the fact they were just supposed to put language together. They're able to, I think, reason better than people thought they would. And so still now, like, I don't think we've been able to get something that surpasses GPT-4 at just reasoning, even if it was not necessarily trained for that.
So I think you're saying that the current language model, they excel at putting the words together to make a complete sentence with good flow. So they only need to maximize the flow of the sentence rather than the logical reasoning of the sentence. In other words, the current model have not evolved the ability to analyze the content and the meaning behind the words, especially in the field knowledge such as math, laws, physics, the subject expertise like these. Uh, and I have heard I have heard methods like a bag of words and a dictionary to train the language model, but they all come down to the combination between words and the frequency of each words, but they hardly consider the reasoning behind the reasoning between the uh, words. So I think this is one reason why the large language model not excelling at reasoning.
Yeah.
And I know also Jan Lucan was like a big kind of skeptic of large language models reasoning abilities, and I know he's talked a lot about that recently as well. And I think he was also a proponent of like kind of again a bit of a change in how they learn, and he doesn't think that the reasoning will be very solid until I think he was talking about their limited understanding of reality, mainly because they're being trained on text as opposed to something like video. But yeah, I don't have a very deep knowledge of his position, but if you're interested, I know that's something that he talks about a lot. Don't know if you've already checked out that. But.
Yeah, they did release a new paper. Facebook released a new paper, which followed what you were saying, like Jan LeCun's idea of how humans think. I haven't read too much into it, but I just posted a link if anyone's interested to read more about it. It's like a switch from the traditional LLM style, LLM style like outputs and just training methods that we're seeing. And it's more like, I guess, what he believes human-like thinking is. Cool, but yeah, I think that like topic is very much up for debate right now, considering how new it is. And there have been some examples where you've seen models like ChatGPT, I guess, think with some form of logic, output some outputs that have like some novelty within them. So I don't think we can completely rule out that they don't have any logical reasoning behind them. I just think it's still new. So like, I guess more and more explorations into the topic are going to begin to reveal that. Cool. Any other questions before we move on to the next paper? I'll take that as a no. Awesome. Okay, let me share my screen. So for the next paper, we're going to be going over a paper that was published in July 2021 by a group of researchers at OpenAI. A paper under the name of Evaluating Large Language Models Trained on Code. And the paper introduces a new large language model named Codex, which maybe Codex you haven't heard of, but GitHub Copilot and GitHub Copilot X you might have heard of. It's been a source of a lot of debate, a lot of discussion, a lot of controversies, been on the news a lot. And the idea behind these models is that they're large language models that are specialized to work with code and like code outputs. So you can kind of see in the GIF on the screen as it like repeats. You like just pass in a specific function that you want to implement, and it gives you a full suggestion, writes down the entire like code line by line for you. And the reason it's been like so up for debate and discussion is because a lot of people are saying models like this are just gonna inherently replace programmers. Is this like the end for software engineering? Is this the end of programming? And so it's like important to know how these models were produced, how these models were trained, and that's what we're going to be going over in this presentation, or like in this overview of this paper. Before we get started, I just want to make sure, is my audio coming in clear? Is my video coming in clear? Am I cutting out? Because I think I'm having issues with video.
It's all good on my end.
Cool. Okay. Some context before we get started. Codex is or GPT, the GPT models are a precursor to the Codex model. Ashley kindly went over GPT models in general, but just to iterate on the important points right now, they're large language models, they're huge, large foundational models, but the issue with them for this specific task is that GPT, like ChatGPT, the GPT-3, GPT-4 models, were trained on a diverse set of data. It can do a lot of different tasks like question answering, like text translation, just in general being like conversational, asking for information, but it's not specialized on one specific topic, one specific domain per se. But the cool thing is, pretty sure some of you might have experienced this if you've been on ChatGPT. Just asked it like a quick coding question, it would give you a pretty detailed response, a pretty good response. And that indicates that even though it is a general model, it does have some hints of being able to work with code, produce code, analyze code, etc. And that's what the OpenAI research team picked up on. And that was like the motivation behind developing Codex, which takes GPT models and just alters it such that it's more specialized towards code. And yeah, so I guess a bit more background. When you want to take an already existing pre-trained model and have it more specialized towards a certain task, you go through a process called fine-tuning. For anyone who's unfamiliar, what fine-tuning is taking that general pre-trained model and then training it using a huge set of data of a different domain. So in this case, it would be something like coding data, such that this model is now optimized to deal with the new domain that you have, coding data, whatever. If like during my Transformers workshop, I took a GPT model, trained it, fine-tuned it, using Shakespearean plays and Shakespearean texts, and now it was optimized to output text in the style of Shakespeare, something like that. But for this case, we're fine-tuning a GPT model using code data. So that brings us to the first challenge that came about with this project, and that is collecting the data set that you need to fine-tune your GPT models. So the data that was used to fine-tune a GPT model to produce a Codex model came from a number of resources. First was GitHub. GitHub, for anyone who might not know, is I guess it's a website that hosts thousands on top of thousands of coding projects and millions on top of millions of lines of code. Millions is an understatement, probably billions, if not trillions of lines of code. So what the what the OpenAI team did is that they scoured the GitHub website for repositories that contain Python code. The original versions of the Codex model was just optimized for Python. And yeah, they were able to get coding data from about 54 million GitHub repositories. That equated to about 159 gigabytes of Python text, which is a lot of Python. And they just filtered out some of the files to make sure that you weren't getting any auto-generated files, any files that weren't really suitable for the training process that we wanted. So that was source of data number one. Source of data number two was websites that us as Waterloo students, we might be familiar with. And those are websites for interview practice, stuff like LeetCode or competitive programming, like Codeforces. The nice thing about these websites and these data sources is that they provide you like data in the exact format that we wanted. The original idea behind Codex, what they initially wanted the Codex models to do, was to take in text data, like a description of a certain function, and then have the Codex model output like a function implementation, output line by line what it thinks, how it thinks the function should be implemented. The nice thing about questions from websites like LeetCode is that they give you a description of the problem that they're asking you to solve. And then they ask you to solve it. And at the end, they give you a full working solution. So you can use that as the label to like compare the output of the Codex model with that full-fledged solution. And another advantage to this, which we're going to get into later on, is a lot of these interview like practice websites and competitive programming websites also include unit tests to make sure that your function works correctly. And that's going to be helpful for us when we're trying to evaluate the output of the Codex models. Okay, that was challenge number 1, the data set. And then once you have this data set, it's time to do training. Like I mentioned, the Codex models were trained, like initially trained to take in a description of a certain function and then have them output how they think the function should be implemented. So when we're training Codex model, we just pass in something like this. We pass in like the description, return list with elements incremented by 1. You give it a couple of examples. And then, of course, you'd have that function already implemented. So when the Codex model implements the function, and when it outputs it, you just compare both outputs. I'd say the training the training procedure isn't really anything special in this case. It's the same training procedure that you'd use whenever you're training any other large language model. You just take in each token, like each, I guess, word that the Codex model is producing, and then you compare it to whatever actual word it should have produced. You do something like cross-entropy loss or negative log likelihood, which is what they used in this paper. So yeah, that's the training procedure. The input is a description of the function, and the target value is the implementation of the function itself. Okay. Now, after we were done with training the Codex model, it's time to like actually evaluate it. Evaluation is a big challenge whenever you're dealing with large language models. Like, how do you evaluate that the output of GPT is truthful, is correct, is a specific flow? It's really hard to perform evaluations on like natural language. However, when it comes to evaluating code outputs, it's a bit more straightforward. You're asking this function that you're implementing to do a specific task. Whenever like Codex is implementing a specific function, you know what the expected behavior of this function is. And so what you can do is you can test this behavior using unit tests. So after all is said and done, when you come to evaluate the model, you just perform unit tests. You give it like a function, you ask it to implement it, and then you evaluate this function based on a set of unit tests. And the way they were able to get these unit tests were either handcrafted, like they handcrafted, I think, a set of 160 like questions with appropriate unit tests, or they were able to take them from the competitive programming websites and the like interview practice websites that I first introduced, or sorry, like that I mentioned previously. And then the third one is a program function trace. This is a bit more complex. What they did was they took like a repository from GitHub. They ran all the code in that GitHub repository. Like it would be like a specific program that runs. And what they do is they look at every single function that gets executed in this specific program. They look at the inputs for the function, and they look at what the function actually produces as outputs, they store those somewhere, and then they ask the Codex model to re-implement that specific function. And to test the implementation of the Codex model, they just test it using the expected input and output that they had previously collected when running the program separately. So that was step number one, crafting the unit tests. Step number two was like actually running the outputs of the Codex model. So it implemented a specific function for us, and now we want to test that it's performed correctly. Unfortunately, like whenever you're working with code, you need to put some like safety measures in place, because the code that you're writing can have like very unintended behavior. Like it could be malicious in some sense. It could ruin like your computer, your host device. It could transmit like unwanted data. And so in order to like be able to safely execute the code that the Codex model was producing, they had to run them in specific environments, which were created using a Google generated tool called gvisor. And then in order to evaluate, once again, the model output, what they did, another interesting thing that they did, is they didn't take just one output of Codex. They asked Codex to implement a certain function, and they asked it to implement it K number of times, like produce a number of different implementations. And they'd run each of those implementations through the unit tests and see what fraction of those implementations actually passed all the unit tests that we wanted. So that was an evaluation metric that they used, which is pass at K. Yeah, in terms of results, one expected thing, like we're asking the Codex model to like produce multiple implementations. So the more implementations the Codex model gets to try out and gets to produce, the better the performance generally was. Like you're guaranteed to get from a couple of those like implementations, a number of them correctly. So that's what we saw as we were like increasing the number of samples that Codex was producing. And yeah, whenever like we gave it a function, asked it to produce 100 samples, it was able to like pass the unit test with about 72.31% accuracy, which when you compare it to a general GPT model, that only passed about 27%. So you are seeing like substantial improvements on the performance of the Codex model. Yeah, that's in terms of results. In terms of limitations, on the other hand, there were two main ones that they discussed in the paper and like other hazards that we're going to go over next. Two of the main like limitations of these Codex models. First was it's not sample efficient. In order to have these Codex models perform really well and produce like accurate code, you really need to train it on a lot of coding data. As I mentioned previously, it was about like 160 gigabytes of Python, like 54 million repositories. When you go to like compare that to like, I don't know, a student learning programming for the first time, you don't really need to look at 160 gigabytes worth of Python data to really be able to like write code properly. And yet, as students, we still perform in many of the test cases and many of the benchmarks way better than what a Codex model does. And then that's limitation number one. Limitation number two is binding operations to variables. Whenever you'd give it a description and you'd ask it to do specific operations on specific variables, it wouldn't be able to tell, oh, am I supposed to do this operation on this variable? Or am I supposed to do it on that variable? For example, we can see this through this example. You ask it to implement this function, do work, and then you give it a description. Tell it add 3 to y, then subtract 4 from both x and w, and then return the 4 numbers. It's able to do the first operation correctly, like it adds 3 to y. But when it comes to subtracting 4 from both x and w, it only does that from x. It doesn't do that for w. And then when it goes to like return the product of the numbers, it just returns the product of Z and W. It doesn't return it for all 4 numbers. So it got confused on like which operations should it be doing on which of the variables. And by the way, that's like another like limitation that you generally see with transformer models and like with some of these attention models. In I believe like the DALL-E image generation model, where you give it like a specific, it's similar to like Midjourney, where you give it a specific text input and then it produces like an image. If you tell it something like, oh, produce a red ball and a blue chair, it would sometimes get confused and produce a blue ball and a red chair. Like it would confuse which adjectives are related to like which of the nouns, which of the objects. So yeah, you see that same limitation here in the Codex model. So that's in terms of limitations. In terms of hazards, like possible disadvantages of using something like Codex, a lot of the code that Codex generates, like superficially, appears to be correct. But when you slowly start to dig into the code itself, you'd realize that there's some small hidden mistake that actually alters the output and produces incorrect outputs. So you really have to be wary whenever you're using something like GitHub Copilot. Double check, triple check your code, run it through a couple of unit tests. Don't just rely on the outputs that you're getting. And that's something that even OpenAI admits in the paper. Like, don't be over-reliant on something like GitHub Copilot or Codex. And another thing is that, like Ashley mentioned for Orca, same thing here applies, is that a lot of these large language models can really be misused to generate like malicious code, to generate pretty harmful content, I guess. So that is a hazard of using something like this. It really gives a lot of power to someone with possibly harmful intentions. And then the third like hazard with, I wouldn't say hazard, it's just a point of controversy with the Codex models and the GitHub Copilot model was fair use. So these models are trained, as I mentioned previously, on millions of GitHub repositories. And it comes down right now to like an issue of, should this GitHub Copilot model give credit to these original programmers that coded the like code that was used to train GitHub Copilot or not? So there's actually a big lawsuit that's going on right now. A number of software engineers filed a like class action lawsuit against Microsoft and GitHub regarding this matter. And yeah, I saw this article, the lawsuit that could rewrite the rules of AI copyright. So it's a pretty big deal. I've left a link for it in the presentation if anyone's interested to read more about that. And yeah, I guess beyond looking at the disadvantages and limitations, just looking ahead, like the bright side to this. A lot of you might have tried GitHub Copilot, saw how useful that was. Microsoft and GitHub recently announced GitHub Copilot X, which introduces like a number of improving features on top of it. Once again, GitHub Copilot X is also like built on top of the Codex model that I talked about. And yeah, it implements like 2 new features, which I think is like really helpful for programmers. It does 2 things which programmers hate the most. And that is, it helps you write documentation and it helps you write unit tests. Like no programmer really likes to do that. So it's really helpful to like do that as well. Plus with GitHub Copilot X, it's a lot more conversational. You can, I guess, give it a specific thing that you want it to implement. It produces like a specific output. You can reply with certain, I guess, fixes that you'd like to see. Oh, this part is incorrect, fix this part. And then, I guess, incrementally update it until you get the perfect output that you'd want and paste that into your code. And yeah, I guess that's it for this paper. Any questions, any concerns, any points of discussion that you guys have?
Someone has their hand raised. Go ahead and go for it. If maybe they put it down.
Yeah, excuse me. I can't really see who has their hand raised. So.
Okay, I think they've put it down. Maybe
Okay.
I'll hop in with a quick question then, if that's okay.
Yeah.
With you saying that there's like, it can produce a bunch of different outputs, like and they can like pick the ones that survive the most unit tests. I kind of had two questions there. It's like, I don't know if they mentioned it in the paper, but if more than one model, like if you do create like more than one output might pass all the unit tests, is there then a selection process for which one to use, like efficiency?
Right.
And then the follow-up on that is just, if in the final version, is it kind of like an OpenAI style thing where you can be like, I want just one response that's the most likely to succeed, or you still get a few and then yourself decide between those?
Right, that's a really good question. So whenever it's producing like an implementation for a specific function, like I mentioned, it produces a number of implementations. And with those different implementations, there's a score called the mean log probability. And that's, I guess in like plain terms, is just a measure of how confident the model was with that specific output. So if you're just restricting it to output one suggestion out of those implementations, just have it select one. It selects the one with the highest mean log probability. But a nice thing with like GitHub Copilot, if anyone's used it, is that when you're like typing something and it gives you a suggestion, you can actually click a button and it gives you like 3 other possible implementations, 3 other possible suggestions as well, and you yourself could get to pick from that. So you get both worlds, I guess. Yeah, you can either just select the one that it's most confident with, or have it suggest a number and then you go and select it yourself. Yeah.
That's neat. You should have gotten sponsored. I'm like gonna go sign up now, so you should have gotten.
Yeah, well, GitHub, give me my money. Cool.
Yeah, I thought.
Yeah, sorry, go ahead.
Yeah, I was just gonna say, I thought the pass at K metric, like I thought that was super cool, and yeah, it makes a lot more sense to, I guess, evaluate based on functional correctness rather than just like matching like a solution, just because you get way more variance in the solution. That's how like in school we're all learning there's like a ton of different ways of programming, of coming up with a solution for different problems. So it just seems like a much better kind of way of evaluating code generation. And one question I did have regarding the I guess the hazards with respect to the legality of it. I know you mentioned, and in the paper it talked about how it was using GitHub repos and it was looking for, I think, like projects that had continuous integration, and like that was how it was getting its unit tests. Was it also like filtering based on like the licenses, or was it just, I didn't actually see it mention anything in the paper about, I don't know, if it was abiding by like licenses. And I imagine like most well created
right.
open source GitHub projects like this that have like continuous integration usually have licenses associated with them. And yeah, it seems like that if they're just kind of taking those to train it seems like a bit problematic.
Yeah, that's a good point. They didn't actually specifically mention it in the paper itself. Like which of those repositories did they take? They didn't really mention licensing specifically. But yeah, like you mentioned, a lot of these GitHub repositories have licenses that not only restrict you from using it for commercial purposes, but also like if you were to use it for a commercial purpose, if it does permit you to use it for a commercial purpose, you have to like give credit to the author. I'm pretty sure like they were mindful whenever they curated the dataset, especially since it's GitHub, it's like the organization that manages all this code. But it seems like that's, I guess, what they did claim in a couple of like posts that they had and like a couple of announcements that they made. But it seems like from this lawsuit, at least, some evidence suggests that they're not entirely like truthful about that. I think that's what the case is that like they claim that they are, but it seems like they aren't through some evidence. And yeah, I guess that's like what the point of debate is right now.
Yeah, no, that makes, because like almost all the licenses have either some stipulation about commercial use or like accreditation about the code. And yeah, it's kind of as you kind of were talking about with like diffusion models, like that's similar in that like should the artist be credited, kind of those sorts of things, right? Yeah, that's
right. Yeah, you are seeing that as well with diffusion models, and there was like this really cool platform, Shutterstock. They're providing people that are training diffusion models datasets that are like from artists that I guess give permission to people to use their art, but in turn, like as many times as like that diffusion model gets used, that specific artist, or they're trying to find correlations relating between the output of the diffusion model and the specific art that was actually used in order to, I guess, pay a certain fee to the artist or give some credit to the artist that actually produced the original work. Yeah. So with that, if no one has any more questions, if no one has anything else they'd like to share, comes the end of the first session of this reading group. Hope you guys learned a thing or two today. Hope you guys found these papers interesting. And this session, we're going to be hosting it again in, I believe we might change up on the time a bit, but it should be in about 2 weeks' time. And yeah, so stay tuned for that. Get excited for that as well. And once again, if anyone has any suggestions for papers or if anyone would like to present a paper themselves, feel free to let us know. Cool. Thank you guys so much for listening in, and we will catch you later.
Bye. Thank you.
Sweet.